welcome to the series on noise control in mechanical systems with me, Professor Sneha Singh from IIT Roorkee. So, we have started the discussion on perforated sound absorbers, perforated panel sound absorbers, and we saw various kind of advantages and limitations. One of the limitations of these perforated sound absorbers or perforated panel sound absorbers was that the absorption magnitude is low. In general it is low because the absorption magnitude is low even at low frequencies or high frequencies. You do not have usually alpha is smaller than equal to 0.8. It is not usually for most of these, it does not go beyond that. So, that is what was initially the case, then it is not worth using them. So, but with the advancement in the manufacturing, we were able to design perforated panels where perforations would be very small in size. You are reducing the size of the perforations. Then a new kind of phenomenon was observed when in the perforated panel itself we have the perforations that are very small in size or sub-millimeter in size, then they are called as micrometer range. Then suddenly the absorption magnitude shoots up. Then what was found was that not just the resonance phenomenon is there, there are additional mechanisms that are coming into play to increase the absorption in such kind of panel absorbers, and hence these new kind of panel absorbers were known as the micro perforated panel absorbers, which we will be discussing in this lecture. So, micro perforated panel, which is shortened as MPP in the literature, most of the times it is a very common term used by the noise control engineers. So, as I already told you that in the perforated panel it was usually the magnitude is not that high. So, various research studies were going on, and initially you did not have that manufacturing capability to manufacture the holes of very small size. But with the advancement in the manufacturing technology, now it has become possible to manufacture the holes which are less than 1 millimeter in diameter. And when such small holes were made in such panels, then what was observed is that when the perforated panels have holes made of these smaller magnitudes, sub-millimeter or less than 1 millimeter in diameter, then new kind of absorption mechanism takes place, and such panels came to be known as micro perforated panels. Okay. It has been sort of highly researched, and a model for that has been derived by the Professor Da-Yu Ma, who is credited for most of the theoretical underpinning in the MPP absorbers. Okay. So, what is an MPP absorber or a micro perforated panel absorber? It constitutes a thin sheet of hard material with numerous such micro holes, and by micro hole I mean the hole which are in micrometer range or less than 1 millimeters. Okay. So, numerous such micro holes that are cut out into it, and the sheet is then backed by the air cavity followed by a rigid backing. So, very similar to a perforated panel, the difference being that now the holes are less than 1 millimeter in size. Okay. So, this also acts like an air spring oscillator. So, let us see the working principle. So, most of the working principle is the same as what we have seen in the case of perforated panel absorbers. So, what is happening? The sound is being incident on the MPP, and then it sets at resonance frequency. There is at resonance when the incident frequency matches with the fundamental frequency. So, at those frequencies this amplifies. So, the air vibrates through these perforations in the panel, and this is through these perforations it goes into the air cavity, which is confined in nature, and hence because of its bulk modulus it tends to oppose the motion and acts like the restoring spring of the oscillator. Okay. And the mass or the small tubes of air act as the mass which is being oscillated. So, the sound energy losses happen due to the resonance. We are setting this mass spring oscillator into resonance, but at the same time there is also some additional energy losses due to the thermos and the viscous effects, or combinedly we call them as the thermo-viscous effects. Okay. So, this is the additional mechanism that comes into play, and this is quite same. So, here in the resonance it is behaving as a mass spring oscillator. The small tubes of air that are oscillating to and fro, the mass of these acts as the mass that is of the oscillator, and the air confined within the cavity with its bulk modulus acts as the spring. But other than the dissipation at the resonance or the resonance based dissipation, we also have the dissipation. So, sound energy dissipation means the loss of the sound energy as heat. So, there is either the dissipation due to the resonance vibration, or there is a dissipation or the loss due to the thermo-viscous effects. Let us see what that is. So, this is same, the neck is the neck in this case of here also the MPP absorbers, they act as a large number of Helmholtz resonators with very small neck, and this thin neck is the thickness of the sheet. Okay, here the neck becomes, or the length of the neck becomes the thickness of the sheet, and the air volume is simply the air volume which is enclosed between the panel and the backing. Now, what is this additional absorption mechanism? The rest of the thing is same as perforated panel. So, what happens is that when the smalls, when these holes or perforations, they are becoming very small, less than 1 millimeters, then the thickness of the viscous boundary layer around the whole orifice, it becomes the similar order of magnitude as the hydraulic diameter of the hole. So, whatever is the diameter of the hole, it is approaching the viscous boundary, the thickness of the viscous boundary layer between that solid and the fluid interface, and hence within this small range, now when the boundary layer and the whole dimension, they are of the same order of magnitude. Okay? Both of them are now of the same order of magnitude, then we cannot neglect viscosity. So, high viscous losses are observed. So, when the fluid is flowing through these perforations, essentially it is a flow of, when the sound waves, they are entering the perforations. It is, what are sound waves? They are longitudinal fluctuations or longitudinal oscillations of the air particles. So, essentially what is happening is that these air particles are oscillating to and fro and passing through these holes, but now the movement of these air particles is being sort of resisted because of the viscous effect. So, there is a viscous drag which opposes the flow of the air particles through the holes. So, high amount of viscous losses happen, and this leads to rise in the absorption magnitude. Okay. So, as you can see here, this is from one paper where they have explained what is it. Okay. So, what we have is that this shows again an enlarged cross sectional view. So, we have an enlarged cross sectional view, and here what we can see is that this is the sheet or the panel and the various holes, and now the viscous boundary layer and the whole dimensions are the same order of the magnitude, and this is how the viscous drag comes into play. It sort of resists the motion in and around the solid surface. Okay. So, because of that what happens is that, and we know that the viscous drag force is directly proportional to del V by del R. So, as the resonance happens, which means that as the acoustic particle velocity or the vibrations, they increase in magnitude, there will be more viscous losses. So, and the vibrations are the maximum at the when the fundamental frequency and the incident frequency are the same. So, there the viscous losses will even increase further. So, at the peak, the viscous losses will be even higher, and the peak will suddenly shoot up and rise in magnitude. So, this shows a more enlarged view. This is the zones of viscous resistance, and this is the overall sort of whole, and what you can see is that proportionally a lot of losses are taking place through these small holes. So, There are some additional mechanisms as well. So, we already studied about what is resonance oscillations and the viscous losses. We also have like frictional losses, which is that the airflow is now being opposed by the friction between the air molecules and the surface of the hole. So, this typical frictional resistance. At the same time, you know, you have some additional thermal and inertial losses, because what is happening is that these molecules or these air particles which are vibrating to and fro, they are trying to compress or expand air enclosed within the cavity as well as, you know, the panel they are hitting, and this periodic expansion and contraction, because it can lead to some thermal losses. But they are not much of consequence. In general, the resonance and the viscothermous losses or the viscous losses, they dominate the absorption phenomenon, okay, and the other form of losses are not having that much significant effect. So, because just like in the case of other resonance absorbers, you know, the fundamental frequency matters a lot, because that is what at these frequencies. So, at the fundamental frequency and its multiples, integral multiples, you should be getting a absorption peak. Okay. So, the fundamental frequency matters. So, therefore, the fundamental frequency of the MPP also needs to be obtained, but because of this viscous effects and the micro size dimensions, usually it is not that easy. You do not have a very easy formulation of the fundamental frequency, you rather have a very complicated model. So, again, you know, the acoustic impedance model for an MPP is quite complicated in nature, and this is for MPP wherever the hole spacing is much larger compared to the radius of the hole. For this case, an acoustic impedance model has been derived. So, this is given by this complicated huge expression here, where the various things, you know, like the coefficient of viscosity, the thickness of the panel, the density and the speed of sound in the fluid medium, the porosity of the panel, the radius of hole and the incident sound wave frequency, all of them are coming into picture. So, all of these are going to affect the overall acoustic impedance of a MPP, and we know that alpha is what? Alpha is 1 minus Z minus 1 by Z plus 1 whole square for the interaction. So, if they are affecting the acoustic impedance, they will also affect the absorption coefficient. So, all of these parameters now are going to affect your absorption. So, this is the acoustic impedance model. When, you know, the spacing between the holes is much larger than the radius of the hole and the incident sound pressure level is smaller than 100 dB. Same model, same conditions, but now with some end correction added to it, and after end correction the new formulation here is that some of the things are changing here. As you can see, this particular character changes and this becomes your new formulation. So, usually this is the formulation that is most used, the one with the end correction. Okay. So, this formulation is something just to keep in mind, because it is a very complex formulation, but when dealing with MPP noise control engineers, they have to remember this formulation. Okay. Now, we know that this is going to give us the surface impedance of the micro perforated panel, but the micro perforated panel does not act alone in isolation. The panel is backed up in most of the cases by a rigid backing or a cavity. Then, so this is the Z of MPP, okay. This is the Z of the micro perforated panel, but the total absorber is composed of an MPP plus a rigid backing, okay, an air cavity, confined air cavity with a rigid backing. So, for that the impedance due to this confined air cavity also needs to be obtained. So, the impedance, the total Z of the micro perforated panel absorber would be Z of MPP plus the Z of cavity behind it. So, you can think of this, you know, that this cavity is like a long tube which is being driven by a harmonic plane wave source, and if you imagine this, just to derive a formulation, you can imagine that this end, the beginning of the air cavity as your x is equal to 0, and here your, so this is your x axis, okay, and here you have the x equals to 0, here you have x is equal to d, and in this one dimensional wave equation you can obtain. So, the pressure wave is given by this formulation. So, it could be a combination of a wave, a pressure going in the forward x axis and a wave going in the backward x axis. So, just a generic formulation is given for a plane harmonic wave. So, this is the general expression for any kind of plane harmonic wavefront in this cavity. If you do the differentiation of this expression, this is what you will get. Now, you can apply the rigid boundary condition. So, at D we will have a rigid backing when the air cavity ends, but here we have the opening because the sound molecule is sort of entering through this. So, there is no rigid backing here, but here we have got some rigid backing. So, rigid wall condition is imposed. So, the velocity here has to become 0, which means that del p by del x has to become 0, okay, at x is equal to d. So, once you have this, you can put del p by del x at x is equal to d as 0. So, when you put this in this equation, so what you will get is that when you put this here, you will get this formulation here. This is what you will end up getting, and you can then obtain an equation for pressure by putting A is equal to B, okay. And once you solve it further, ultimately what you will end up getting is that you will get this kind of a wave equation, okay. And then you can use some properties of the acoustic medium which in the acoustic fundamentals module we had studied, that rho naught del u by del t is minus del p by del x. So, you can use this property and you can find out the equation for the acoustic particle velocity. You already know the equation for the acoustic pressure. Then P by V is going to give you the Z. So, you can do the P by V at x is equal to 0 to get the surface impedance of this cavity. Once you solve this expression, this is like a home assignment that you can do. The derivation is kept here, but I am not going into the details of it. So, just the step by step what you need to do, and when you put P by V, this is what you are going to get, okay, ultimately. So, anyways, the end result is going to be, once you follow this process, step by step, you take a generic expression of the pressure wave, you put the boundary condition as at x is equal to d, your velocity is becoming 0, which means that the pressure gradient is going to 0, and then you solve, you get an equation for P, you solve further, and then you use this particular property and find the equation for V, and P by V you get and solve it. So, this becomes your Z of cavity. So, with this what will happen, now you know this formulation. So, you can simply say that the Z of MPP is already known by this formulation, and now the Z of cavity is known by this formulation. So, you can get the total impedance of the MPP sound absorber, and once you have this, then you can find out the absorption coefficient. So, as you can see, it is very complicated and very complex. So, a straightforward solution is not there. Usually people use various kind of data driven approaches and techniques to actually solve the impedance of the micro perforated panel, and for this particular lecture course, we are not going to go into the detail of what kind of data driven approaches are actually used to solve various MPP based kind of problems where you find out the absorption coefficient of an MPP. It's not within the scope of this particular introductory lecture. So, just you see the expressions, and in the next class we will see that based on the expressions that are derived, what is the effect of the various parameters on the overall acoustic impedance, and what is the effect of these parameters on the absorption coefficient. Okay. So, with this we will close the first lecture on MPP. Thank you.